Okay, so we're going to take a quick look at the idea of projectile motion and how that looks relative to the motion that the object is experiencing moving horizontally and vertically. So let's imagine that we are looking at an object rolling off the end of the table. So here's our table, and let's imagine here's a floor, that we have a ball, and it's rolling off the table. Now, from our experience, we probably expect that as soon as that ball leaves the edge of the table, there's nothing holding it up. So it's going to start falling. So it starts to fall. But it also has motion horizontally, so it doesn't fall straight down. I mean, it is moving to the right. So it also continues to move outward or horizontally. Now, if we think about what the shape of that motion looks like, well, we notice that we would draw a trajectory, sort of an arc. Actually, it's a parabola, specifically. So what gives rise to that motion? And how can we use what gives rise to that motion to have an understanding of how motion in an object in projectile motion can maybe be analyzed as we move forward into the analysis phase. So let's break these two pieces up. First, let's look at the falling part. Well, why does it fall? Well, this is the same idea as free fall. The object is no longer interacting with the table, and it's no longer interacting with anything as soon as it leaves that table, except the force of gravity. So we know that as soon as it leaves the table, it's in a state of free fall. If we think about what free fall was from our previous experiences with free fall causes an object to accelerate, and that acceleration was in the vertical direction at a constant, that negative 9.8 meters per second squared. So the ball, or whatever's rolling off the table, whatever's in projectile motion, is experiencing this acceleration in the vertical direction at negative 9.8 meters per second squared. It's only in the vertical direction. We talked about free fall being only under the influence of gravity, and gravity only acts in the vertical direction, so the acceleration piece is happening vertically. Now, if that didn't exist, what would the ball do? Let's imagine for a moment that the acceleration piece didn't exist. Well, then the ball's just going to keep going. There is nothing to change its motion in the downward direction, to have that acceleration in the downward direction. And so the motion of the object falling itself, coming down, is vertical only. This is key. Only vertical. Now, what about the fact that it keeps moving to the right? Well, nothing is changing its motion to the right. Nothing's influencing that motion to cause any difference as the object continues on. So there's no change in motion horizontally. The acceleration horizontally is 0. Nothing is affecting its motion horizontally. It's just going to keep moving horizontally. So it has to move both horizontally while it moves vertical. And if we think about the acceleration as sort of a comparison between these two directions, horizontal and vertical, we can see that they're different. The object is experiencing an acceleration vertically, but it's not experiencing an acceleration horizontally. So what that tells us and what that gives rise to that we're going to use, which is a very powerful thing when we talk about analyzing projectile motion, this all gives rise to this idea that horizontal and vertical motion are independent. That what happens horizontally is completely independent of what happens vertically. So even though this ball is falling down vertically, accelerating down vertically, and in this case, speeding up as it moves down vertically, nothing's happening horizontally. It's independent. It just keeps going on, going on, going on. And in the amount of time it would take it does take for this object to fall to the ground would be the same amount of time that it would take the object to move across to that same location if it wasn't falling to the ground. So they're completely independent. Now we experience this frequently, right? So imagine that you're walking along, tossing your pen or your whatever, the ball that you're carrying, up and down. How do we throw that object when we're walking? If I'm moving at a constant rate and I toss my pen up and down, while it's with me, it's moving at that constant horizontal velocity with me, that horizontal one. So even when I toss it up, it maintains that horizontal velocity, the same horizontal velocity that I'm maintaining. So the amount of time that it goes up and back down, I am moving horizontally. And if we're maintaining the same horizontal velocity, then it is going to move horizontally by the same velocity that I am, and therefore the same distance that I am. So if I want to be able to catch the pen, I have to throw it straight up. It already has the horizontal component of the velocity that I have. It's not going to be influenced horizontally, and so I will move at that same steady rate. The pen's horizontal motion will also move at that same steady rate. It's just going to go up and down. The vertical is independent. So what does that look like pictorially? Let's try to draw what I've just verbally described. And admittedly, I'm not going to be able to draw a hand very well. So let's instead imagine that we have a ball moving on a cart. All right, so here is this little, I'm just going to make the cart like that. And we have a ball inside. Now, the ball, the velocity of the ball is in that direction. The velocity of the cart is in that direction. Both are horizontal at this point. And we know the velocity of the ball is equal to the velocity of the cart. They're traveling together. So let's imagine at some point in time, further along, the ball is shot straight up from the cart. All right? So as the ball is shot straight up from the cart, well, if we look very closely at what its velocity is, the velocity of the ball at this point, well, it still has the horizontal velocity that the cart did. But it now also has a vertical velocity. So what does that look like? Well, if this is my velocity vector, I have a component of the velocity that's horizontal and a component of the velocity that's vertical. Now, it's a true velocity now has both components. But and therefore, what direction does it go? Well, it starts to go up. If this is, here's its true velocity vector, right? The component of both of those. So imagine for a moment that it can escape the cart. And we see that it starts to move to the right and up. Well, as it moves up, if it's only under the influence of gravity, the velocity in the vertical direction, as it's moving up, acceleration is down, it's going to start to slow down. But the velocity in the horizontal direction is uninfluenced. So as this ball moves up, it starts to move in a projectile fashion, as we suspect. Then, if my cart continues to move in the same velocity that it had before, horizontally, and the ball has that same horizontal velocity, without it being unchanged, it's going to move along horizontally at the same rate the cart is. And as it leaves the cart horizontally, it'll cover the same distance and should land back in it. Just like as I toss my pen, if I toss it straight up, it will cover the same horizontal distance that I am walking, because horizontally we're moving together. If I were to toss it in front of me, now I'm giving it an extra horizontal velocity. I'm increasing the horizontal velocity forward. It now has more horizontal velocity than I do, and it'll land in front of me. If I toss it behind me, if I toss it backwards thinking, well, it's moving forward, I want to slow it down so I can catch it. No, if I toss it and cause the horizontal velocity to be smaller, so I give it a little acceleration that way, decreasing the horizontal velocity, then I'm going to be moving faster horizontally than the pen. I won't be able to catch it. So the only way for me to be able to catch that pen is if the pen maintains the exact same horizontal velocity that I'm maintaining, which means I can't change it at all, and I can only throw it straight up. And that truly is foundational in this idea that the horizontal and vertical motions are independent, completely independent. What's influencing vertical motion doesn't affect the horizontal motion at all. All right, so we're going to use that idea to solve problems. We're going to make projectile motion problems really, really easy. We don't have to worry about how the velocity vector is changing if we accept the independence. All we'll do is separate those two directions independently and analyze horizontal motion completely separate from vertical motion. Then we just have twice the motion problem to analyze, but we're very sophisticated at that already. So, independence for projectile motion, remembering that things are in free fall, that only then affects vertical motion. Horizontal motion remains unaffected, and we can look at the two objects, or the two directions, independent. All right, good job.